Hey guys, welcome to our first AP Chem video of the year. We're going to sort of do things a little bit differently than maybe last year we did in Chem 1, and so there will definitely be some video stuff, but there's going to be some lecture stuff in class also, and I'm going to try to make those things supplementary and things that maybe are a little bit confusing in class or that I know that we'll need some extra backup on or that people missed a lot of. I'll try to make some videos as well. So not everything will go into a video, but if you feel like you need some help, of course, make sure that you let me know and I'll jump in and try to assist you on that. What we're going to talk about today is combustion analysis, and basically this is an outgrowth of empirical molecular formula. So you guys learned how to calculate those in Chemistry 1. If you're a little foggy on that or you're not sure, hit that QR code there or go to the YouTube channel, search the Arnold Science channel, find Vodcast 8.5 from Chem 1, run through that. We'll do a little empirical molecular straight up at the end of this video, but that's not really the heart of what we're going to do this time. It's kind of assumed that you know that. So if you don't, go back and fill in those gaps, and then that'll help us to do this combustion analysis. So the way combustion analysis works is that we're going to take a sample, usually some sort of hydrocarbon, and it could have some other stuff in it as well. But the way these problems are a little different is in a normal empirical molecular formula problem, we're given just several percents, and then we're just asked to calculate what's the empirical formula, what's the molecular formula. In a combustion analysis, you're not given percents, and in fact, you're not given straight up elements that just says you have this many grams of this element, you have this many grams of this. Instead, what you have are compounds given. You've got a mass of the original compound, and then you've got a mass of a couple of products as well, and then you have to do some further calculation to really figure out what's going on. And so this is kind of the setup. So we put a sample in there, okay? We're going to burn it in the presence of oxygen, hopefully excess oxygen, because the calculations don't come out very well if it's not excess oxygen. And so then what would happen in the real world is that there would be a device here. Essentially, there would be one part of the device that would absorb all the water, and this would kind of help us to know how much hydrogen was in it, the original sample here. And then we'd have something else that would absorb the carbon dioxide, so something like sodium hydroxide here. This might be something like magnesium perchlorate or something like that that would absorb the water. And then out the other end will come oxygen and some other gases. But these two steps are really what's vital for us. And so I think, as with many AP problems, we're going to jump into the math here, and it will hopefully help to explain the conceptual part behind that as well. So this might be a sample problem. So we've got 0.1156 grams of a compound. That compound contains carbon, hydrogen, and nitrogen. Okay, so that makes this a little bit more complicated. The nitrogen part will make this a little harder than some of the problems. And we're going to react it with excess oxygen. Now again, that excess oxygen is important because that means that the main products are going to be carbon dioxide and water, as opposed to carbon dioxide, carbon monoxide, and a bunch of other garbage. Okay, we want that excess oxygen or in abundant air or something like that. And what is produced is 0.1638 grams of carbon dioxide, 0.1676 grams of water. Now this makes it a little harder. If it just said it was this many grams of carbon and this many grams of hydrogen, then we could easily just do a quick calculation and figure out the nitrogen. But this is going to be a little bit more complicated. So again, we've got our sort of setup here, and this is what's going on. But if you look at this, here's the way it works. We're going to, all of the carbon that was in this original compound, okay, so that was in this original amount of 0.1156, all of that got turned into CO2, okay? And then all of the hydrogen, okay, in this same compound got converted here, okay, into water. And so these two assumptions are going to lead us to our calculations, okay? So what that means, if we look at the information that we're given here, okay, let me erase a couple things here real quick. What that means for us is that this number, okay, this 0.1638, all of the carbon has to be in here, and all of the hydrogen has to be in here. Now, obviously, there's more than just carbon and hydrogen in those two things. There's oxygen in both of them. And so what we sort of have to do is try to figure out what part of this is carbon, what part of this is hydrogen, and then what parts of the original compound do they add up to, okay, so that we can figure out the percentages, and then we can do empirical molecular formula the same way we did. All right, so let's dive into this and look at this. So if all of the carbon had to be converted to CO2, okay, and remember that that amount of carbon was, and we'll just write this up here just so that we remember it, all of the carbon turned into carbon dioxide, and so there was 0.1638 grams of CO2. Okay, now what we need to know to be able to calculate this is, first off, we have to know the molar mass of CO2. And again, I'm sure that everybody in AP chemistry doesn't have any problem with that. Carbon's 12, oxygen 16. There's 2 of those, so that's 32. We add those together and we get a molar mass of 44, technically 44.01, okay, grams per mole if we're going to be a little bit more precise. Now, why does that matter to us? Because we know that 12 of those 44 grams are carbon. Okay, so let's go over here then and work that out. I'm going to make a conversion factor, so this part should seem pretty familiar from Chem 1. So 12.01 grams, let me make that decimal point a little clearer, are carbon in 44.01 grams of CO2. Okay, now remember that what's important to us, or what our given is this guy right here. Okay, this is the amount of CO2 that we have that's produced in this particular problem. So 0.1638 grams of CO2. Now, of course, that's a simple conversion factor problem. We cancel out what we can cancel, which in this case is grams of CO2. We're left with grams of carbon, which is good because if I know how much of one element I have, then I've got something to do percentages from, right? Okay, so then we punch that into our calculator. We do all that math. Remember, 0.1638 times 12, all of it divided by 44, and that's going to give us an answer of 0.04470, or 0.0447. Okay, grams of carbon. That's a 7, not a 2. Okay, just to make sure. So that's good. Now we know how much just of one element, so now we can talk about a percent. So how do we turn that amount into a percent? Well, we take that 0.0447 grams of carbon and we divide it by the original sample. Not this amount, but by what the original sample was, which is this, the 0.1156. Okay? So we come back over here. We've got 0.1156 grams, and we're just going to call this the compound. Okay? And then we want it to be a percent, so we're going to multiply it by 100. Remember not to hit the percent key in your calculator. That'll mess everything up. Okay, and so we calculate that out, and we have 38.67% of carbon. Now this is good because, again, once we have the percents, then we can do the empirical molecular formula pretty easy. Okay, so 38.67% of carbon. Now let's do the hydrogen. Remember, our assumption is that all of the hydrogen was converted to water. Of course, I don't think that anybody needs to be told that water is H2O, but just in case, that's what it is. That means that 2 grams of it are hydrogen, 16 grams of it are oxygen, and of course the total is 18. So that much of what? So what was produced? Well, if you look back on that problem, it's 0.1676 grams of water were produced. Okay, so we're going to basically do the exact same calculation we did the last time, except now we're going to do it for hydrogen and water instead of for carbon and carbon dioxide. So I start with 0.1676 grams of water. Okay, again, that was given to me in my original problem. And I want to turn that into hydrogen because I'm trying to find the percent of just hydrogen by itself. Okay, so the molar mass of water, and if we really wanted to be precise, we could do this. Really, if you'd done 18, that would have been fine. And remember, on the AP exam, you're not going to have a calculator anyway, so you're not going to be able to probably carry it out to these decimals. But the book did, so I was trying to be as precise as possible. That's the hydrogen part. Okay, so again, cancel what cancels. Grams of H2O cancels. And so that is then going to leave us with 0.01875 grams of hydrogen. And again, since that's by itself now, it's just hydrogen, we can take that and divide it by the total, the original sample, and we can get the percent of hydrogen. Okay, so 0.01875 grams. Whoa. Sorry guys, it's been a long time since I had to write with a pen. That's what happens when I make apes videos all last year. okay, of hydrogen divided by that original total. So what was that original total again? Remember, it was 0.1156. That's the original sample. That's the compound, okay, times 100 again. Okay, equals, that's an equal sign, equals, okay, and that's going to equal 16.22% of hydrogen. So now we have our percent of hydrogen. If we went back a slide, we have our percent of carbon. And so what don't we have? We had carbon, hydrogen, and nitrogen. But the good thing is if there's only 3 things and I know 2 of them, then I know the percent of the third thing, right? So the remaining percent has to be nitrogen. So we just take 100 minus what we've already found, which is 38.67. Okay, and remember that's the carbon, plus 16.22. That's the hydrogen. Okay, we subtract that out, and that's going to leave us with 45.11%, and that is nitrogen. Now here's the cool thing. Now, okay, now that we've done all this, this is a regular empirical formula problem. I know the percent of carbon, I know the percent of hydrogen, I know the percent of nitrogen, and so now this is just your everyday empirical formula problem. So I'm going to go ahead and work that out, but if you feel like you already know how to do the empirical formula, you don't really need to watch everything else in the video, but I'm going to take a couple extra minutes and go ahead and run through those last few steps. So, how do we do the empirical formula part? Well, real quick, remember that we just take each of our percents and we drop the percent and we just assume that we have 100 grams, so that becomes grams of carbon, and we divide it by the gram atomic mass, or the molar mass of that, whoops, sorry, turn my pen off, grams of carbon over 1 mole. Okay, so that's going to give me 3.220 moles of carbon. We're then going to do the same thing for the hydrogen. So we've got 16.22 grams of hydrogen divided by molar mass of hydrogen. That's 1.008. Sorry, that's all funky looking. That's a little better. Grams of hydrogen, 1 mole. Okay, and that in that case we're going to get 16.09 moles of hydrogen. Again, in decimals. We got problems. Okay. And then the last thing is the nitrogen. Remember that we calculated by subtracting it from 100. So 45. That's a 5.11 grams of nitrogen. Molar mass of nitrogen, 14.01. And again, guys, don't panic. If you plugged in 12, 1, and 14, really not going to make any substantive difference. And in fact, if you had to do this on a test, sans calculator, then I wouldn't sweat it. Don't use the 14, use the 1, use all that. You're going to have to make some sort of rough approximations then, because you're not going to have time to actually work everything out on paper then. So remember, this is the step where we take the smallest of these numbers and we divide everything by it. Really, these are pretty much the same number, but technically 3.219 is the smallest one. 3.219. Divide them all out there. Okay, that's going to leave us with a whole number of 1, with a whole number of 5, with another whole number of 1. So that means that our empirical formula here is CH5N. Okay, so that's our empirical formula. Now we could take that one step further. We could have been asked what is the what would actually be the molecular formula. And so in that case, if we knew what the molar mass was, we could then calculate what the molecular formula was. And so remember, the way we do that is we take that empirical formula that we had, and we're going to calculate the molar mass of that. Remember that that would be the EFM. Okay, so 12, 5, because 1 times 5, and then 14. And so we add all this up together, 19, and that's going to give us 31 grams per mole. And really, the way that this would work is we would take our molecular mass here, 32.0 grams per mole. We would divide it out, and you should get a whole number. In this case, we're not going to get precisely a whole number, but it's going to be close enough to 1. And so what that would mean is that our empirical formula of CH5N actually is our molecular formula in this case. Now, if this number had been something like, say, 62, and we did this math, then it would have come out to be 2, in which case we would have multiplied all of our subscripts by 2. Okay, guys, that's 15 minutes, a little bit over what I wanted to have, but hopefully that gives you a good idea of how to do combustion analysis, and obviously we'll work a bunch of these in class together in groups until everybody's got a pretty solid handle on this. Thanks, guys.